All right, physics students, we're going to talk about energy in the next couple of lectures. And we spent some time talking about work, and I'm going to show you how work and energy are intimately related, but they are not the same thing, okay? And I just want to start off with a very basic question. What is energy? And the bottom line is nobody really knows what it is. We know how to harness it. We know the effects of energy. We know how to give things energy. But nobody really knows what energy is. So if you want to win a Nobel Prize, go for it and figure out what energy is, okay? Now, I'm going to give you a somewhat of an esoteric definition of energy, as I did with work, and I'm going to say that energy is something which enables a body to do work, okay? And the SI unit for energy is the Newton times the meter, which is a joule. Symbol is J. We talked about that before when we talked about work, okay? So again, the joule is the unit for energy and work, but work is not equal to energy. They're intimately related, and here's how. So by giving something energy, we give it the ability to do work. So for example, my calculator, I lift it up, right? I lift it up a particular height. I have given it the ability to do work. If I let it go and it falls down and hits the table, it's going to do work on the table, or it's going to do work on my hand, which is on the table, and it's going to hurt because it's going to exert a force over a distance on my hand. It would never have been able to do that had I not given it the done work on it and given it the ability to do work on my hand. Okay, so I gave it energy by doing work on it. Okay, so the other side to think about would be when doing work on something, we give it energy. The two of them, you see how they are intimately related, okay? And there's lots of examples in everyday life, okay? So in the first case, this guy's doing work on the basketball. He's throwing the basketball up. Okay, he's given the basketball the ability to do work on something else, which is the floor. This guy over here pushing the car, he's doing work on the car. The car then acquires energy and is able to do work on something else. Like if it hit the side of the building, it would do work on the side of the building. Same thing with a rocket launching, okay? So there's this whole idea of energy and work is critically important in your understanding of physics. Okay, so I want to talk about some common everyday kinds of energy, okay? The first, which is probably the most common, is potential. And we say PE or E sub P, either of them, okay? And this is stored energy within an object. And there are different ways that objects can sort of acquire energy and store energy within them. The easiest one, the one you're most familiar with, is gravitational potential energy, GPE or E sub P. This is the energy stored in an object by virtue of its position relative to a source of gravity. In other words, if I lift this calculator farther away from the center of the Earth, it is acquiring more gravitational potential energy than it did before when it was on my desk, okay? Chemical potential energy. This is energy stored in molecules that can be released in a chemical reaction. So when you eat your cereal, your grape nuts for breakfast, that cereal actually has energy. It has potential energy, and when it gets into your stomach, there's a chemical reaction. Your body knows how to get that energy from that food, and that's why when you look on the side of a package, like all food basically has nutrition information. It talks about the amount of energy in that food, and they actually talk about calories. A calorie is another unit of energy. We don't use calories in IB physics. It's not the SI unit for energy, but be aware that a calorie is just another unit for energy the way a joule is, okay? Electric potential energy, EPE. This is energy stored within electric charge and an electric field. Elastic potential energy, we'll talk about this one. Energy stored within a flexible object or spring when stretched, okay? All right, and that pretty much, there's lots of other different kinds of potential energies, but those are the sort of big ones, okay? Second most common is kinetic. KE or E sub K. This is the energy of an object due to its motion. And third, thermal, a combination of kinetic and potential at the microscopic or molecular level, dealing with heat transfer and the way that molecules jiggle and move really fast within the substance. We'll talk about that later. Okay, so in this particular topic, we'll mainly focus on kinetic and gravitational potential. We'll talk a little bit about elastic potential. Okay, and I want you to do the reading by Feynman that I've put on the study guide on the web page. Okay, that's a really good one. Okay, so let's first talk specifically about kinetic and potential energies. Okay, now if doing work on something gives it energy, say this basketball, if I lift this basketball, if I do work on the basketball, I lift it up, I've given it energy. Okay? And we do W equals mg h naught on a basketball to lift it to a height h from the ground. Okay? And by the way, notice in this case theta equals 0, so the cosine of theta equals 1. So in all my work calculations, I'm never going to consider cosine of theta because it's just equal to 1. So I don't really have to think about that. Okay? All right? Anyway, I do W equals mgh naught on a basketball to lift it all the way up here, and I let it go. It can do a certain amount of work on something at distance h naught below, right? That's the same situation as my calculator, okay? All right, so really this should be a negative sign there, as I talked about before in the previous video, because it's two different things doing work. We don't really care about the negative sign, but it tells us that different things are doing work, okay? Now, we gave it energy. And when we gave it energy equals mgh naught, exactly equal to the amount of work we did on it to lift it, okay? This is the gravitational potential energy. It is the work done by gravity, or the work done by you to counter gravity, depending on the way you think about it, okay? That's exactly it. Okay, now specifically, if my distance is h naught minus hf, as in this diagram, and the force applied is the weight of the basketball, the work done on the basketball by gravity would be W equals Fs times mg times h naught minus hf, which is mg delta h. And that is exactly the gravitational potential energy of the basketball in lifting it from here to here or going from here to here. It doesn't matter. Negative or positive, doesn't matter how you think about it. That's the actual energy, or the energy difference of the basketball. Now in your IB data booklet, you have that this is the equation for energy. I believe it's delta E. You see often you see delta E. It's because it's a change of energy, and it's also important to think about how it's relative to something else, which I'll talk about in just a second. Okay. Now, if work equals gravitational potential energy, which is mg delta h, turns out this is called the WorkEnergy Theorem. Super important in physics, and it will come up over and over and over again. When a net external force does work W on an object, the energy of the object changes from its initial value to a final value, the difference between the two values being equal to the work done. I read that fast, so you should probably pause and read that again. It's very important that you get that, okay? It's basically just saying that the work done is equal to the gravitational potential energy gained or lost by something. Now, work and energy are not the same thing, but they are equivalent in this sense, okay? Now, when determining the gravitational potential energy, you need to choose the zero level. Usually it's the floor or the ground or something else convenient. Therefore, gravitational potential energy is always relative to some other location, since it is only the change in vertical position that is important. Normally, we take the bottom, the final height, as 0, such that GPE is mgh, okay? Where hf would be 0, and h naught, we don't even call it h naught or h max or whatever. We just say it's from 0 to some distance h, okay? Note that the path the ball takes to get from h naught to hf does not matter, because only the initial and final positions are important, okay? Very important. Okay. Again, the importance of a zero reference point. I have a mass on a table. The height of the table is 1 meter. The ceiling, or there's some line up here that's 2 meters. If we consider the tabletop the zero reference height, then the gravitational potential energy is 0. Okay? When lifted to the 2 meter mark, the mass acquires 19.6 joules of energy to go all the way up here. If we consider the floor the zero reference height, then originally the potential energy of the mass is 9.81 joules. When lifted to the 2 meter mark, the mass acquires 29.4 joules. Okay? Notice that either way, the change in energy is the same. Okay? So it doesn't matter. Doesn't matter. You want to be smart students, and if you can ever have a zero reference point where actually one of your points is actually 0, then that's great, because then you'll deal with zeros in your equation and things will get a lot simpler, okay? But you do not have to do that if you don't want to, all right? Okay, again, when you lift a mass, the work you do do on it goes into the gravitational potential energy of the mass. The mass can then do work on something else. It has acquired energy exactly equal to the work you did on it. I cannot reiterate enough how important that concept is for you guys to understand. Okay, now your data booklet tells you that delta E sub P equals mg delta H. Okay, again, that's what I was alluding to before. It's the change in energy. It's better to put the change in energy if you're going to put the change in H. Okay, all right, one of my favorite examples of all time. Try this one on your own. I'm asking you about a pendulum and the GPE of the mass as shown. Okay, interesting problem. Okay, what's the gravitational potential energy of the mass as shown? Well, you can define your zero reference point to be anywhere you want. I think most people would probably define the bottom of the swing as being a height equal to 0, where the gravitational potential energy is 0. So therefore, we should have a positive value, which depends on this particular height right here as shown in the diagram. Now, the length of the pendulum is 1 meter, and the mass is a half a kilogram. Okay, I don't know what answer you got, but let me show you how I did it. Okay. I noticed that, well, you're going to have to figure out what this distance of h is. Okay, that's crucial for figuring out the gravitational potential energy. Notice that this particular spot right here, okay, all of this right here is L cosine theta. You see that? This is L cosine theta. If this is L cosine theta. Now, turns out that the height is L minus L cosine theta. Okay? You get that? See that? Where this is the right triangle right here? Okay, that's 0.0795 meters. Again, taking the bottom of the swing as h equals 0, then I get a gravitational potential energy of 0.39 joules. Okay, now, in a somewhat ridiculous case, I don't know if any of you wanted to do this, but you can if you really want to, because you're really dealing with delta E, delta gravitational potential energy. If you take the roof or the top of the pendulum as the zero reference point, you would get a GPE of negative 4.9 joules, okay? Again, that's arbitrary, okay? And if you were to take that to be the case, you would find that the change in gravitational potential energy over this height right here would still be the same as it was before, which is 0.39 joules. Okay, now, consider a constant force accelerating a plane over a displacement, okay? So here's a plane taking off on a runway, displacement here, initial velocity u, final velocity v, a constant force, okay? Since the force is constant, a is also constant, and we can use one of our equations of motion to come up with an expression for a. And displacement, we can also use another equation of motion, 1/2 v plus u times t. Now, using the expressions for work and force and combining 1 and 2 above, note that work is force times distance. Force is ma from Newton's second law, mas. Now I've substituted a up here, this expression for a here, and this expression for s here, and I end up with 1/2 m times the quantity v minus u times the quantity v plus u. Okay? Now, if starting from rest, where u is 0, this ends up being 1/2 mv squared. Guess what? This is the kinetic energy. I have derived an expression for the kinetic energy of the jet for you, or the change in kinetic energy, delta Ke. And it's 1/2 mv squared. You probably know this equation before, you've seen it before, but you never knew where it came from. Here you go, it's easy, okay? And again, your data booklet, there is no delta here. It's just E sub k is 1/2 mv squared, so be aware of that. Okay, try this example on your own, example 2. Okay, the amount of work required to change the speed of this particular car from 20 to 30, okay? The work is equal to the change in kinetic energy, which is Ke prime minus Ke. This is the final kinetic energy minus initial, okay? Notice that I can factor out the 1/2 m. I get 380 kilojoules in this particular case, all right? Okay, try this example. An electron is acted upon by an electric force, accelerates it from rest with a kinetic energy of that, not very much. If this is done over a distance of 3 centimeters, find the magnitude of the electric force. Again, straightforward. F is delta Ke over S, which is W over S. I got 1.7 times 10 to the minus 17 newtons. Okay, here's one that's a little more interesting. Try this one. the skier going down a slope. Okay, ignoring, this is a situation where we have to deal with frictional forces. And remember, that's a very important, we cannot neglect friction in this class. We deal with it from time to time. Specifically when it's stated, you have to deal with it, okay? Determine her speed at a point that is displaced 57 meters downhill, okay? All right, so what I've done is I've drawn some vectors on the skier herself, okay? So here's her weight vector. I've broken the weight into two different components, okay? Here's the frictional force. Here's the weight, the component of the weight pulling her down the slope, okay? All right, now gravity does work on her equal to Fs, but it's only in the vertical, okay? And I'm taking positive to be down the slope. The net force on the skier then would be mg sine 25 degrees minus F sub k, okay? Right, it's this force minus this force, okay? Now, the work is equal to F times F, or the sum of those forces times S, okay, and that's equal to the change in kinetic energy. And that's 1/2 mv squared minus u squared, okay? So all I do is I solve for v, okay, and I plug things in, and I get that she's going 19 meters per second, okay? So you want to, if you don't get this one, it's a little more complicated, pause and go through my answers again. Okay, before I end this video, I just want to talk a little bit about springs and elastic potential energy. I alluded to the fact that elastic potential energy is one of the potential energies that you need to be aware of, okay? And in my previous video, I talked about an equation that's in your IB data booklet. I'm going to show you where that equation comes from right now, okay? When you stretch a spring or any other stretchy thing like a rubber band or a rope or whatever, you give that spring the ability to do work on something else. Think about if you stretch a rubber band and shoot it at your friend. When that thing hits your friend, it hurts because there's a force being applied over a distance on their flesh, and they don't like that, and they'll probably hit you. Therefore, when you do work on a spring, you give that spring energy, okay? Now remember, F varies as S varies, since F equals Ks, and we had this Fs graph that looked like this, okay? We saw that the work to extend a spring from x1 to x2 was 1/2 kx2 squared minus x1 squared. The equation in your data booklet comes from taking x1 equal to 0, and so that's our equilibrium position. Okay, so it's pretty simple. So in that case, the work is the elastic potential energy, which is 1/2 kx squared. I believe in your data booklet, it's 1/2 k delta x squared. Be aware of that difference.